the cloud. All right. So today we're going over binary search. Okay. This is so cool. So things to know about binary search. Let's share a screen, shall we? So things to know about binary search. It will only work when the data is sorted. Okay, so this is what we want to do when we're searching for something is, let's say we have an array. Let's make our array something like 1, 1, 12, 22, 44. Can I put 36?
No.
No, because that's not sorted, right? 55, 59, and 60 random numbers. Let's use the assignment operator there. Okay, and so this has to be sorted. And so, okay, so someone says, hey, I'm going to give you this array, and I'm going to give the number 58, and I want you to tell me what index 58 is on. Okay? So we look at 0, 1, 2, 3, 4, 5, and we should give back 5 because 58 exists on index 5. Okay? And so this is the goal of of a search, right? And if I say, hey, I want to know where the 2 is, this would give back -1, right? So this behaves very much like the results where if we said like index of, and I put 2, right? This gives us back -1. And that's kind of like a standard in JavaScript, but not in every language. So just be aware of that it just depends on what you want back. But we see like, hey, index of 2, since there's no 2, we get back a -1. So you may be thinking, well, if I really want to do this, I could easily write a function called like search, right? I could write search that takes in an array and a target. And I could just say like, hey, for let element of array, if my element is equal to target, return, oh, I actually need the index, so let's change that. Sorry. I was thinking just of it includes there for a second. So while I is less than array.length, I plus plus, if array at I is equal to target, return I. At the very end, we'll be returning -1, right? So now we have the search method, and I can pass in our array, and I can pass in 2. Let's console log this. And we get our -1 here. We'll put our 58 in here. And we get our 5. Okay. So who can tell me what the time complexity of this method is?
Linear.
Linear. Yeah, thank you. What about 500?
I'm kidding. It was a joke.
Okay.
Bad Jeopardy memories.
Oh, yeah, baby. I love Jeopardy. Okay. Oh, man. Henry, Rafid is throwing some shots at you.
Not throwing no shots.
Shots fired. What sarcasm. Okay. So this is linear. Now, this would be okay if my data was not sorted, right? But my data is sorted, so there's a way for us to make this way more efficient, right? We don't need to search every single one in order to search for something. That'd be silly. That's like the phone book example where I give you an M someone like Mary and you start in the A's and just keep going to the B's, to the C's, to the D, right? That would be such a waste of time. If you were with a friend and they said, oh, look up this girl I'm seeing, Mary Matthews, and you start in the A's and then you went to the B's, your friend would be going, hey, idiot, jump to the middle, right? Like everyone would take the book and flip to the middle because you would want to be doing it quick. And so that's how our binary search is going to work. And so if you ever hear or see a algorithm problem or question and they mention that the data is sorted in some way, your first thought should be, I wonder if I can solve this with some kind of binary search. If it's in any kind of sorted thing, maybe it's all increasing to decreasing or decreasing to small to big, big to small, or maybe it starts small and it's going to peak in the middle and then it's going to end small and you're going to be looking for a peak, right? That's still a form of sorted data, right? Because the largest number is going to have smaller numbers beside it. If it's some type of sort, you should be thinking, is there a way for me to incorporate binary search? Because binary search, we talked about, has a time complexity of log n. Okay, log n, so that's very short. So let's look at a visualization of what binary search is. Okay, here we have all of these numbers. We have numbers 1 through 20, and these are the indexes of the array. Okay, as you can see, these are sorted. Let's say we want to look for this element 2. Okay, we want to see if element 2 exists within this array. You go, okay, so let's go ahead and step. So our first step is we look in the middle, right? Because we just want to see in the middle. We see, okay, we have a 10 here. Now, is 10 greater than or less than our target?
Greater.
Less
Right.
than.
No, 10 is greater than our target.
Oh, greater, yeah.
Our target is 2. So we go, okay. So we know our target can't live on this right side. That has to be a fact because the data is sorted. So we know for sure our target lives somewhere in the left side here. So we're going to update our search and look for the middle of this half. So it's going to look like this. And we look at 5 here. Now, is 5 greater than or less than our target?
Greater.
Greater.
That's right. 5 is greater than our target. So that means our target can't live on the right side. So the target has to live somewhere on the left side. So we're going to cut our array again and look in the middle. And we end up getting 2 because of the way they're doing their division. Okay, and so we go, okay, key 2 is at index 1. Okay, let's try again. This time, let's look for something bigger. Let's look for the number 12. So we have our array here, and we start in the middle, and we say, okay, is our target larger than our target, right?
Right.
And we go, yeah, we're currently at 10. So we know it has to live on the right side of our data here. So we make our step, and now we look here, and we see here, and we go, okay, now we're at 15.
Oh.
Now our target is less than 15, which means we're going to have to look at the left side of what's left. So we'll make our step, and we end up at 12. So in just 3 moves, we were able to find that 12 exists in this 20 numbered array. And finally, if we look for something outside of there, let's see if this works. We start at 10. We know we got to go further. So we'll step. We go, okay, this is still smaller than our target. Let's go to the right more. This is still smaller than our target, still smaller than our target, still smaller than our target. 25 is not in the list.
Corey.
Yes.
So regarding how you just put 25 right now, in the logic itself, right? If you already know that the number is not in the array or it's outside, why would it keep doing the half? Wouldn't it already just shouldn't it go to the last number in the array first and see if that's greater or less than that number you're looking for, and then decides it's undefined or not, or it's not possible to get that number?
Good
Yeah,
question.
so that's an interesting optimization that you're talking about. Is like, can't I just check the min and the max and see if it's at least within the range?
First, yeah,
Yeah,
just to make sure.
you totally could do that. That's fine. It's we're looking at like the average case.
Gotcha.
So with unknown series of numbers and all that. So the average case, the time is log n. So it doesn't really matter. But if you have like the small group or something and we really don't know what the range is or anything, then yeah, I mean, you could that could definitely be a small optimization, but it's
Okay.
not required for most binary search things.
Okay.
That's a good question. Any other questions on what binary search is? Okay, so let's go ahead and try to write one. So how we're going to do this is I'm going to talk us through the pseudocode of this, and then we'll split into breakout rooms and try to write it ourselves. Okay, so let's first do the iterative solution. There's iterative and recursive, of course. Also, there's probably a binary search question on the exam. Okay, so.
Can you repeat that again, please? We didn't catch that.
Nope, I cannot. Sorry. I think
okay.
you caught what I said. So, okay. So we can start with, if we think about it, we have our array and we can start, how do we find the middle of this array?
Split it in half.
Getting the median?
Okay, yeah, right. So we could split it in half. Median, I don't know enough about math. I forget what that means. I think it means middle, right?
Yeah, it means middle.
Okay. But we don't care about the numerical middle of the context. So we just care about the middle of the array.
Can we do the math floor?
Math
and then
floor.
divide and then divide the array by 2, I think.
Okay.
The length by 2.
The length by 2?
Mm-hmm.
Okay, we could do that. Now, but let's pretend, okay, so let's pretend that we did that and we're looking for the number 12 again. Okay, so we've divided the length by 2 and we've looked and we're at 10. So now how would we update the next middle?
You would have a condition
Okay, tell me more.
saying you would have to compare at this step which side is closer. So either are we going to look at the left side or are we going to look at the right side? And then once we determine what side we're going to look at, then we can step again. Then we can do the length between the length divided by 2, given the 2 increments, the side that we're on.
Yeah, but how will we know the length here?
Go to like we can find out the index of where we landed and go from there to the end of the array and then split it.
Wouldn't we have to just fire whatever we did to divide the thing in half again? Like we can, like, you know, you mentioned we can do this recursively. If we are writing a function where we are dividing the largest array in half to get the middle the first time, then we'd have to save those 2 halves into variables somehow and then do it again.
Well, we don't need both halves. We only need the 1 half because we're certain it's not in the other half.
Yeah, and then we got to fire the function again and just keep breaking it down until we get our target, right? So our target's got to be like our base case.
Yeah, we could do something like that. So that's if we're going to do kind of recursive. What about if we had 2 pointers? What if we had a left side that started at 0 and a right side that started at the end of our array length. And so we could update our pointers accordingly.
Mm-hmm.
How does that sound like that might work?
And we'll like stop it when they hit the same thing, right? Like when they meet in the middle, that's when we'll stop it. And then we'll see what that number is. And then if that matches our target, or if it's greater or less than our target, then
Yeah.
we'll have whatever side that we'll need to do it. And then we'll just run that function again to get that next middle.
Well, we won't need to run the function again. This is iterative, remember
Right.
that?
Oh yeah, right.
In some kind of while. So maybe we have a left side and a right side pointer, and we think like, hey, while our pointers, while our left is less than our right, find middle, check if target found, update pointers. Okay? This is the hint. Okay, this is the bulk of the logic. Let's go into our breakout rooms and try to write this out over the next 10 minutes. Okay? So I will just add another room. Okay. Let's do it for 12 minutes. Okay? But act like you got 10, so you got a little fire in you. All right? See you soon. Okay. Awesome. Yeah, way to go. Okay, so let's go over this together. So let's share our screen. That's directed at me. That instruction. And okay. And so let's follow our steps and see how we do. I'm gonna move our array lower so we can like watch it around too. Okay. So let's go ahead and walk through it. So we're gonna start here and we're gonna go const. Let's call this B search for binary search, for iteratively. And we know we're gonna take in an array because that's the whole point. And we know we're gonna take in a target because that's what we're gonna be searching for. Also the whole point, right? And so now we have to create these left side and the right side pointers. So if we look all the way to the left of our array, the very first index we'll ever deal with is 0, right? We know that, that's a fact. So we say let left and we'll assign that to 0. For the right side though, we don't know how large that array is. So we're gonna have to look all the way to its length and do the -1. So we'll say let right be array.length -1. And we'll go -1. So we go, okay, great. So now what we can do is we can say like, hey, while our left is less than or equal to our right, because we still want to check if they end up at the same for this one. Although sometimes you don't want to. It's kind of like a one-off thing. It depends on this equal to or not equal to. Sometimes gets changed depending on the problem, I've noticed. But we could say, okay, so while our left is less than or equal to our right, we want to do some stuff, right? And we know we're eventually going to return the index in here. And if we don't find anything at the end, we'll go ahead and return our -1. We know that because if we escape this while loop, naturally, we didn't find it. Otherwise, we'll return out of our while loop. So we can go, okay, let's see. Find the middle index. All right, well, we can find the middle index by simply adding up our left and right together and dividing that number by 2. So we can say left plus right divide by 2. Can anybody tell me what problem we might run into though with this?
Yeah, if it's an even number, it's going to give us a decimal. So
An
we're
even-
not-
If it's an odd.
number.
I'm sorry, if it's odd number, yeah, it's gonna kind of
Ah, it's an odd number. Yeah, right. So because if these added up to 7 and we divide by 2, we get 3.5.
Yeah.
No, we don't have an index at 3.5, right? So
Nope.
let's just do natural integer division and go ahead and round our number or floor it. I prefer flooring because that's integer division is done with flooring. Rounding rounds up, but like, so 3 can't go into 5 3 times, which it can only go in a max of 2 times, right? Does that make sense? Like 5 divided by 2, let's say. How about we just do it that way? 5 divided by 2 gives us 2.5. So if we round up, that's 3. But 2 can't go into 5 3 times. That's not true. 2 can go into 5 2 times. So because of that, that's called integer division. And I'm going to round down. Ruby does this naturally. So I'm going to floor it here. Okay, so now we have to check, like, hey, is the element at this middle index, is this actually equal to our target? So we say, hey, if array at mid index is equal to our target, well, then we're done, right? And we can just go ahead and return our mid index. We have successfully found our element. Otherwise, we got to make a decision here, right? We can check if it's larger or smaller. So we can say like, hey, if array at mid index is, let's say, less than our target. I'm just choosing that one. It could be the other. So if this is less than our target, which one of our pointers needs to get adjusted?
the right.
Thank you.
Tell me more about that. Why is it the right? So let's think about what this statement means here, right? So let's say I'm looking for the number 55.
Oh,
And I'm on the number 22.
yeah, it's the left side.
You're going to the left side and you're gonna
So,
add
right, our left side's got to be added. So, and I can add 1 because I don't need to check the middle. Exactly, Henry. So I'm going to go ahead and update. Let's be left is equal to mid index plus 1. Great. Otherwise, if it's not equal and it's not less than, we can be certain that our number was greater than. So I'm not going to make a condition. I'm just going to say else if, and I'm going to update our right to be our mid index minus 1.
Yeah.
And believe it or not, that's it. That's this whole binary search problem. So let's go ahead and test it. So we'll say console.log b search iterative. Let's pass in our array. And let's go ahead and look for 11. Let's try the bottommost range. And we see it's the 0th index. Let's try 58. We'll try like the top. Near the top. That was the 5th index. Let's try a number that's not in there. Let's go with like a 13. We save it. We run it. And we get our -1. So it's safe to say, I mean, it's relatively safe. I mean, we could have a lot more tests, right? But it's safe to say that this is correct. Any questions on how this is working?
So the binary search only works if the numbers are like from least to greatest, and there's only like a unique number, right?
Not necessarily. It only works if it's sorted in some way. This could be sorted the other direction, and I could write a binary search concept. It would just be written in the other way. So you have to know how it's sorted, right? So this is the traditional binary search where it's sorted in increasing order. But if we know that the data is sorted in non-increasing order, then we can write it to accommodate that kind of data. If we know that the data is sorted in a way that it's going to reach a mountain peak, then we can deal with that as well, where we can see if this number is greater than its neighbors and how it relates to its neighbors. So we just have to know how the data is sorted to write it. Was that the whole part of your question?
Yeah, and then the unique part.
Oh, the unique part. No, it wouldn't. I don't think uniqueness. Uniqueness. You'd have to update it depending on what was wanted with uniqueness, right? So if they wanted if there was non-unique numbers and they wanted the first instance of that number, you would be doing your binary search until you found an instance, and then you would probably just iterate back from there, or do a left side binary search from there or something. You would have to update your search in some way, but
Okay.
it just depends on what the requirement is. Typically, in a lot of these, the data is unique, or the data you care about is going to be unique. All right.
Can you explain why we're reassigning left and right by middle index +1, -1?
Sure. Well, we've already checked to see if that middle index is our number. We did that here. It's not, so I never want to accidentally check that again. So I'm going to the next number that hasn't been checked in both directions. No need to duplicate that check. Again, depending on the type of binary search problem, sometimes you don't want these. Sometimes you only want one of them, and then you return the right side. You'll see. So let's think about how we could write this problem recursively. There's a couple ways. We could keep a left and right index recursively as well and keep passing in the same array. We could also slice and cut the array. Slice is technically an n operation, right? So defeats the purpose a little bit, but it's still fun. So let's split back into our breakout rooms and try to solve this in a recursive way over the next, let's go another 12 minutes. Okay?
New HHA.
So I'm going to just move you into group 6. Okay. I'm just moving some people. Okay. I will see you all. Oops. Hang on. I'm sorry. Okay. I will see you all soon. minus 1. Hey, oh, there. How you doing? Which I don't know if you can hear me. I can't hear you. Which room do you want to be in?
Hello, Corey. What's your background?
That was right, Danny.
Is Pee Wee Herman's Playhouse?
Of course, you play Pee Wee Herman. Why am I not surprised?
Oh, Maria, that's quite the silhouette.
Yeah, I was about to say this.
Oh, I'm wearing my I don't know if you guys know that hoodie that's also a blanket.
Oh my god.
No, I don't know those. That's
The Snuggie?
Yeah.
I was like, whoa.
Snuggie?
Danny wearing one of those?
Yeah, you know. Why not?
Yeah. Oh man. Scale 1 to 5. How did this go? How did this go for you? Recursive implementation. How
Can we
did
get
this
more
go?
time?
What?
Can we get more time? Is this the time thing?
No, this is how did it go. If
Wow.
everybody needs
So
more
close.
time, I can give more time.
So, all right.
But I was kind of hoping to finish lecture soon so that people can work on more binary search problems on their own. So, okay.
Working on it together is
What?
Working on it together is definitely helping.
Oh, well, people can still work together. Just, I mean, like multiple problems.
Okay.
Okay, let's share the results. I think, yeah, looks like we got a pretty nice distribution there. Mostly on the positive side of things, so that's good. Let's go over this one, and then I'll let everybody go. And there's some practice problems for you to work on, and one that I suggest working on. Okay. So let's do this. Share the screen. I'm recording, I'm pretty sure. Okay. So I'm just gonna move this iterative thing here. Just to keep these together. Okay. So let's go ahead and write a B search recursive. Let's call it Wreck, like Wreck-It Ralph. Great movie. If you haven't seen it, very, very good movie. Very good. Not as good as Sling Blade, course. Well, it depends on your taste, like all things. Sling Blade was very good. Thank you to Jenya and Nilber, who both watched it and gave my movie choices a shot. Appreciate that. Picking up some street cred. All right. So we've got, let's do, so there's a couple different approaches, right? The first approach is we can cut this array in half. It's actually not as intuitive as you may think. I think the other way is a bit more clear, which is where we can still have pointers. So let's do the pointer one first, and then we'll do a little bit less intuitive one with the cutting. Actually, we'll do the cutting because that one's worse. That's the worst solution. So, okay. So we have our array. What's a good base case for this? What's the smallest input that we could put in and know the outcome for sure?
Yeah.
Empty array.
An empty array, yeah. And what would that mean for us?
Wouldn't we not return anything, right? Because we don't have an array, then we don't have
-1. You could return -1, right?
-1.
Good, return -1, right?
Yeah.
So excellent, right? Because if our array is empty, if we truly have an empty array, we know for sure our target can't exist in that array. I think that logic is fair.
Yeah.
So we go, okay, great. So let's go ahead and find our middle index, right? Because we got to get that middle. Got to get that mid, right? So we'll say mid index. And we got to still do our math.floor. So we're going to do integer division. And we can just do array.length divide by 2. There we go. Okay, great. We've got our middle index. So what's the first thing we care about? What's our first check?
See if that middle index is your target.
Yeah.
Specifically to see if that middle, if the element at that middle index is our target. So we can say, hey, if array at mid index is equal to our target, we can just go ahead and return our mid index. All right? We go, great, no problem. So let's go through the different scenarios though. So like, hey, if array at our mid index is actually going to be, let's say it's greater than the target. So we're here and our target was 11. What needs to happen?
Then
If our target is 11.
We have to decrement that index, don't we?
There's no indexes here.
Oh.
Well, we just have our mid index, but
We will have to go negative mid or -1 mid.
well, you guys are like taking the easy route. We're still trying to write a binary search. What if I'm right here, and my element is here?
so then we'll have to like search that part from like 0 to 55, right?
That's right. We got to look for that left half
The left
of
half.
the array, right? And I can go ahead and return that. So I'm going to say b search rec, and I can just go ahead and do my array.slice, and I can go from 0 to my mid index
The mid, yeah.
and pass in my target. Go, okay, cool. So this is where it gets a little less intuitive and a little more interesting, which is on our right side, our else case. So if it's not on the left, it's on the right, right?
Right, yeah.
So why is that interesting? Well, why can't we just say b search rec array.slice from my mid index and my target? Why can't I just return this? Anybody know? Well, let's see. Let's try it. If we don't know, let's try it. Okay, so I'm just gonna move this down here. Let's do one where we have to look on the right half. So let's go ahead and look for 55, shall we? We'll update this to be our rec. Okay, what do we expect? What's our, or let's say 58, because we've done that one a few times. What's our expectation?
Hit the index of 58.
Supposed to be 5.
Yeah, 5, right? That's
5.
what we're hoping for.
Mhm.
Instead, I get 2. Let's think about it.
Because it takes 55 becomes like the beginning of the array.
Okay, so let's see. 0, 1, 2, 3, 4, 5, 6. We'll go to 3. 0, 1, 2, 3. So we look here, and then we've sliced here.
Mm-hmm.
And now we're calling it on this array. So 0, 1, 2.
Mm-hmm.
And this is our answer.
Oh, okay. I see what it's.
So we're sending back this array and getting back the answer for this array. So that's because 4 divided by 2 is 2, right? That's not ideal. So what can we adjust?
The index.
Okay, so sure. So we need to do a little bit of math here, right? We need to still keep track of where we were. So we do need to add our mid index, right?
No.
Because our mid index here will be where we sliced it. So let's try that. And we go, okay, why did that not work?
It'll go in the else.
Yeah, it's on the else case.
Oh,
you put
I'm
it.
sorry. Yes, thank you. Got mixed. Okay. I mean, it's not supposed to actually work, but it's going to work for this scenario. Okay, so we do this now, and we go, oh, okay, we got 5. Great. This is great. What's wrong? Let's try something that's not in the array. Let's try 77.
Yeah.
Oh, well, we got a maximum call size exceeded. Interesting. Wasn't totally expecting that, but
I think you were expecting it to like add to the -1, right?
that's right. I'm expecting it to add to our -1, and it's not. That's not a good thing. So instead of just, yeah, go ahead.
But your rule on line 38, right? It's just saying if there's an array, right?
Yeah, I'm just checking to see if it has a length.
Yeah, it's not gonna go to -1 because you didn't set it up to be -1 if your target is not there. You don't have a rule for that. Am I bugging?
Well, if I did
Right, yeah.
23, well, it's freaking out, but it's not because of that rule.
Alright.
It's just that this doesn't really work.
Okay.
But what we can do instead is we can save this as a variable called res or const, right? It's probably better practice. And I can check here if my res is -1 or not. So I can say, return, hey, is my res equal to -1? If it is, let's go ahead and keep returning -1. Otherwise, we can return our res plus our mid index. And this should work. If it doesn't work, there's something else weird going on. There is. What's wrong with this code?
The base layer, the base condition is off. Oh, wait, sorry, oops.
Hang on, what the heck? I wrote this code earlier. Oh, I didn't, let me just check something. Let me see if it works on the code that I wrote earlier. I might just have a minor. Oh no, I get the same the same bug. Interesting. So how do we fix this? This is not the way I personally like to write B search, just for the record. So we have to figure out why our call stack is getting to be too much. And I'm going to say it's because this should be mid-index plus 1. And I'm going to save that. And I'm going to try again. And now we get our -1. And let's try, because we just keep getting that last element instead of moving past it to get an empty array. So that's why that was happening. So let's try something too big though now. Let's try 79. And we get our -1. Let's try something that's really in there. And I think we're still going to hit a bug, and I'm hoping we do. Ah, we get this 4 on our 58. So what's not that intuitive here is when we split this, this is index 2. But that's because this index is being counted, this index, sorry, so 0, 1, 2, we have 6, right? So 0, 1, 2, 3. And so we're getting this back. So we have our 3 is our mid-index plus whatever we're going to get back from here. And from here, we get back our 1. Right? And so 3 plus 1 is 4, which is why we're getting this outcome. But that's because our 55 is being counted as a 0. So what we actually have to do is say res plus mid-index plus 1. Okay, that's actually going to work. And that will work for all of them. So we can also do 12. I mean, the left side's obvious that it works, but the right side will also work. No. Okay, I know that's a little confusing of the logic there, but essentially with every time we take the right side, we have to also keep track of the mid index and then that 1 to make up for the new 0th index of that new array. That's all that is, because indices are 1 behind. That being said, yeah, I can take any questions on this here. If not, I'll move on to the other and better way to solve this. Okay, so let's do this recursive the second way, and we'll style it a lot more like our original bsearch iterative. So let's call this brec2. So let's say const our bsearch rec2. And this is going to take in our array and our target. Okay, and we also need this left and right. We're going to keep track of these pointers, right? That's going to be our goal. So we're not going to be slicing the array because that takes too long. That's not really keeping our algorithm efficient. It's not really utilizing our binary search. It's a good thing to see. It's a good thing to practice, but it's not really the best use case. So let's go ahead and add our left and our right. So I'm going to say left, and I'm going to default that to 0 because I don't expect my user to call that. And I'm also going to pass in a right. And I'm going to just default that to my array.length -1. Very much like the way our iterative one. Now, our iterative one ended when left became greater than right. That's when that ended, right? We broke out of our while loop. So we can do that same thing for our base case, where we can say, hey, if left is greater than right, let's just go ahead and return our -1. Because we know we haven't found it. Otherwise, let's go ahead and find our mid. So we'll say our mid index again, and that's just going to be the same math from here. So I'm actually just going to take this whole line and toss it in. Okay, so we've got our left plus our right divided by 2. And then I need to make some checks, right? I got to check if this mid index is in fact the correct spot. So I'll say, hey, if array at mid index is equal to our target, we can just go ahead and return our mid index. Else, we got to see, hey, is our mid index greater than our target, let's say. So, hey, if our array at mid index is greater than our target, well, then we want to call this again with just update our right side to be our mid minus 1, right? Just like we did in our original here. We're doing the else statement. We did right equals mid minus 1. So in that, I can just go ahead and return my B search rec2, where I pass in my array, my target, my left, and my mid minus 1 as acting as my right. Now, if I haven't returned yet, the only other option is the other one. So I can just take my B search call, return B search, but this time this would be mid plus 1, and this instead would be our original right. And if we do that, let me move our array so we can see it and look at it.
Corey, is it mid or mid index?
Yeah. It's a mid index. Thank you. Got carried away. Okay, and so let's take a look when we try brec2. And we can go ahead and see that that gives us back our 6. Let's try the lower bound. We get 0. Let's try something that's not there. So we'll try 23. We get -1. We can try something that's greater than anything in there. We get our -1 and something that's less than anything in there. And we should get -1. So to me, this brec this B search rec is quite a bit more clear than the other one. I don't have to worry about that hidden extra 1 and keeping track of that middle. Instead, I can just see if my left is ever greater than my right. I didn't find it. Otherwise, I'm grabbing the middle. I'm going to check if that middle's our target. Otherwise, I'm going to check if it's greater. If it is, I'm just going to update my right pointer to be my mid minus 1. Else, I'm going to just update my left to be my mid index plus 1. I know it's a lot, but it's pretty cool. This is log n. And if you ever see a problem where it says, hey, think you have some sort of data that you're trying to find something or do something with, you should be thinking, why did they tell me the data was sorted? Every problem, like most problems don't have red herrings in them. Some do, and like maybe it doesn't help you, but a lot of problems, they are giving you that information as part of the clue to use. So if you're just like, all right, I'll just do a linear search, like, great. Is there a more efficient way to do this? You know, like, oh yeah, there is.
So if they give us a question with arrays and they opt the back just say, you know, let's give an array, find this value or this part of the index. I could ask the interviewer like, hey, are the arrays sorted or not, just to make it easier for myself, right?
Yeah, you could ask if the array is sorted. That's another thing. If you're ever given a problem with an array, you should be thinking like, how will I solve this? Is there a data structure? Can I use an object to help me keep track of things to make this faster? If not, can I sort this array to make things faster to help me? So there's always these options. And you should always try to go through them as part of this like pattern, right? If I said to you, hey, there is a 100-story building and I want you to drop, and you have a basket full of eggs, and at a certain level, the eggs will start to break. tell me which floor the eggs start to break in the least amount of moves. You know, breaking the least amount of eggs. Well, you could start on the very first floor and drop an egg, right? You could start on the second floor and drop an egg, the third floor and drop an egg. But then you're doing a linear search. That's a B search problem, right? I could go to the middle of the building and drop the egg. If the egg breaks, go down halfway. If the egg doesn't break, go up halfway of that half, right? So these problems exist all over the place, all the time. Sorry?
No, I was just like I never thought about it like that. That was actually kind of that's crazy. Like I never thought of an
These
answer.
problems are hidden everywhere. And so, I'm going to stop the recording. And without further ado, I have some problems for us somewhere. Okay. I would work. This is a cool problem. I'm posting it in the chat. I'm also going to post this in our Slack channel. This is a problem you should work on. There may be a problem similar to that one on the exam, without the weird syntax, but with a similar concept. And then let's see, here in our Pursuit Core DSA, here I'll share the screen so you can see what I'm talking about. This isn't really a lab for you. You don't have to turn anything in. This is just something you should definitely practice. These kind of things do show up in interviews like all the time. So in the DSA, you'll see here, this is our curriculum. This is like the core lessons. Today we learned binary search. And so you can look here at the standards reassessments, and you can look at these different problems of sections. Today you should work on the DSA 5B binary search problems. These are, I think, are mostly links to LeetCode code problems, but they are good problems to work on. Okay, so take the rest of the day, work on those, work with each other, ask for help if you need any help. Okay, any questions at the expectation? All right, see you later. Thank you. I'm still recording. Whoops.